Welcome to this lecture on the introduction to mass spectroscopy. Today we begin one of the most powerful and versatile analytical techniques you will encounter in this course, a technique that has earned 4 Nobel Prizes and underpins and fields from drug development to environmental monitoring and planetary exploration. These 6 objectives frame everything we will cover today. 1 and 2 are definitional, the language, and the architecture. Item 3 is the vacuum, which is the one piece of physics that is truly non-negotiable in mass spec. 4 and 5 give us metrics we will use to compare instruments, and 6 is the applied skill. By the end of the lecture, you should be able to read an instrument spec sheet, read a problem statement, and make a reasoned match between them. Our path through the material is relatively straightforward. We ask with the question, what is mass spectroscopy? We tour its history, short but important, because the landmark instruments we will use today trace lineages back more than a century. Then we move to the modular architecture with every single mass spectrometer, regardless of manufacturer, fits the same 5-block diagram. If you understand the blocks, you understand the technique. Then finally, we finish off with our worked example and practice problems. Let's begin with the simplest possible definition. Mass spectroscopy is the measurement of the mass-to-charge ratio of ions in the gas phase. Every mass spectrometer ever built does exactly this and nothing else. Notice 3 important words. First, mass to charge, not mass. We measure the ratio, not the mass directly. For singly charged species, which are extremely common in modern biological MS, the ratio can be much smaller than the mass. We will see how to deconvolute that in the next lecture. Second, ions. We do not measure neutrals. This is why every mass spectrometer begins with an ionization source. If a molecule is not an ion, we cannot see it. Third, gas phase. Ions must be desulfated, floating freely in vacuum. You cannot put a solid or a liquid into a mass spectrometer. You put in samples that get converted to gas phase ions inside the instrument. Everything in a mass spectrometer is about doing those 3 operations well: ionize, separate, detect. The whole rest of the module is just variations of those 3 fields. Why is mass spectroscopy such a big deal that 4 Nobel Prizes have been awarded for its development? Let me walk you through the capabilities that make it unique among analytical methods. First, mass accuracy. A modern orbit trap routinely delivers 1 to 3 parts per million mass accuracy at a typical mass of 500 daltons. That means plus or minus 2.5 thousandths of a dalton. With that accuracy, you can often determine the exact molecular formula of an unknown. No other technique can do that for a molecule you've never seen before. Second, sensitivity, attomole. That is 10 to the minus 18 moles. For a molecule of moderate size, that's somewhere around a few hundred to a few thousand individual molecules. You can genuinely detect single-digit numbers of molecules on a good LC-MS system. This matters enormously for trace analysis, doping, drug metabolism, environmental contaminants, and so on. Third, structural information from fragmentation. We will cover this in a lecture 4. When you fragment an ion in a controlled way, the fragments form a fingerprint that is often diagnostic of the structure. Fourth, chemical specificity. When you combine high mass accuracy with an isotope pattern check and a fragmentation spectrum, you effectively confirm a compound in the same way NMR does. Before we dive into the physics, let me give you a sense of where this technique actually lives in the real world. Pharmaceutical quality control is probably the single biggest industrial user. Every batch of every drug that reaches a pharmacy shelf has been characterized by mass spectrometry at some point in its development or release testing. The nitrosamine crisis a few years ago, when contaminants in valsartan and ranitidine were discovered, was entirely a mass spectroscopy story. Specifications are measured in parts per billion, and MS is the only technique that can deliver that. Environmental applications have exploded in the last decade. The PFAS story, forever chemicals in drinking water, is driven entirely by LC-MS methods, with detection limits of 1 nanogram per liter. Dioxins, an EPA priority pollutant, are routinely measured by highly resolution mass spec. Food safety is a major area, especially in countries with significant agricultural exports. Pesticide residues, mycotoxins like alpha toxins in peanuts and rice, and so on. Let's take a moment to rewind back to 1912, because the modern mass spectrometer starts here. J.J. Thomson, who had already won the Nobel Prize in 1906 for discovering the electron, was working at Cambridge on something called positive rays, beams of positively charged ions produced in low-pressure discharge tubes. He set up a clever arrangement where ions pass through crossed electrical and magnetic fields before hitting a photographic plate. The physics is this. The electric field deflects the ion by an amount proportional to its charge divided by its energy. The magnetic field deflects it by an amount proportional to its charge divided by its momentum. When you plot the two deflections against each other, each value of mass to charge ratio traces out a different parabola on the detector plate. Thomson's most famous experiment with this device used neon gas. Neon is supposed to be a pure element with atomic mass 20, but Thomson saw two parabolas, one at mass to charge ratio 20 and a fainter one at mass to charge ratio 22. The second parabola had no business being there if neon really was a single pure substance. This observation was the first direct physical evidence of stable isotopes, and eventually led to the understanding that most elements are mixtures of isotopes with slightly different masses. I want to spend a moment on the century-long arc of this field, because the hardware we use today has so many parents. After Thomson, the first really important advance came from Francis Aston, who was Thomson's student. Aston built what he called a mass spectrograph in 1919. The first purpose-built Aston built what he called the mass spectrograph in 1990. He got the Nobel Prize for this in 1922. In 1934, In 1934, Martok and Herzog designed the double focusing sector instrument. Double focusing means it corrects for both energy spread and angular spread in ion beam. With that design, you can reach resolving powers of 10,000 or more. Sector instruments remain the high-resolution workhorses for about 50 years. Jumping ahead, in 1953, Wolfgang Paul at Bonn invented both the quadruple mass filter and the three-dimensional ion trap. These turned out to be the right designs for cheap, compact, low-resolution instruments. Today, every GCMS in a modern lab is a quadrupole. Paul shared the physics Nobel in 1989. This slide is the single most important organizing principle of the entire module. Please commit this diagram to memory. Every mass spectrometer ever built, regardless of price or manufacturer or application, has these 5 modules in exactly this order: sample inlet, ion source, mass analyzer, detector, data system. Let me walk you through them from left to right. Module 1, the sample inlet. This is how the sample physically gets into the instrument. For a gas or a volatile liquid, it might just be a sealed septum with a tiny pinhole. For real applications, it's a coupling to a chromatograph, either gas chromatography, which we call GCMS, or liquid chromatography, which we call LCMS. The combination of chromatography plus mass spectroscopy is called a hyphenated technique, and is the single most powerful tool in modern analytical chemistry. Module 2, the ionization source. This is where neutral molecules become ions. This is the subject of our entire lecture. Choice of an ion source is arguably, of our next lecture, sorry. The choice of an ion source is arguably the single most consequential decision in designing an MS method. Pick the wrong source and your analyte never reaches the detector. Module 3, the mass analyzer. This is where ions of different mass to charge ratio are separated in space or in time. There are 6 major types of mass analyzer: sectors, quadrupoles, ion traps, time of flight, orbit traps, and FTICR. Each has its own niche. That's lecture 3. Module 4, the detector. The detector's job is simple: turn arriving ions into a measurable electrical current. We'll touch on detectors in Lecture 3. Module 5, the data system, just a computer really, but an important one. It converts raw ion counts into the mass spectrum you see and controls the entire instrument. Notice the dashed envelope around modules 2, 3, and 4. That's the vacuum envelope. The ion source analyzer and detector all live inside a vacuum chamber pumped to between 10 to the minus 5 and 10 to the minus 10 millibar. That is far below atmospheric pressure. In fact, it's lower than the pressure on the surface of the moon. We'll see in a few slides why this vacuum is non-negotiable. When we introduce a new technique in the rest of this module, I want you to ask yourself first, which block does this belong to? ESI is a 2-block item. The quadrupole of block 3 and an MRM experiment is a specific way of operating block 3. If you always orientate yourself on this diagram, nothing in mass spec will ever feel disorienting. The first module, the sampled inlet, is often taken for granted, but it's worth understanding what it does. For a very simple instrument, say you're tuning an instrument with a pure calibration compound, you can just push it in directly. A septum in a reservoir works for gases and volatile liquids. A direct insertion probe works for solids. You put a tiny bit of sample on the tip of a heated probe, slide it into the vacuum chamber, and heat it to drive off the vapor. For anything more complex, and realistically that's 99% of actual analytical work, the sample inlet is a chromatograph. Usually either a gas chromatograph coupled to the MS, which is GC-MS, or a liquid chromatograph, which is LC-MS. The reason this matters is that real samples are mixtures. Blood, food, river water, reaction mixtures, everything is a mixture. And mass spectrometers have a very specific weakness when faced with mixtures. The process of ionization is competitive. If two compounds enter the source at the same time, they fight each other for charge. One of them wins and ionizes, the other one loses and does not make it to the detector. This is called ion suppression, and it is the single biggest reproducibility problem in mass spectroscopy. The solution is chromatography. The chromatograph spreads the components of the mixture out in time, so that at any given moment, only one compound, or at worst, a few compounds, are entering the ion source. That directly improves ionization efficiency, solves most matrix effects, and makes quantitative MS possible in real samples. We will return to this in Lecture 5 when we cover hyphenated techniques and the LCMS MRM workflow in detail. I'll tease the next lecture briefly here. The ion source is where neutral molecules become ions, which is the whole prerequisite for everything else happening. Sources fall into two categories based on how much energy they deposit into the ion. Hard sources, of which electron ionization is the classic example, deliver a large, well-defined amount of internal energy to the molecule. That drives extensive fragmentation. You see lots of fragment ions. That's great if you want to figure out the structure. The fragments are diagnostic. It's bad if you want to see the intact molecule because often there's barely any molecular ion left. Soft sources deliver very little internal energy. The molecular ion mostly survives intact. The spectrum is simple, sometimes just one peak. That's great for measuring molecular weight and for quantitation. It's less useful for structure elucidation on its own, though we can follow up with fragmentation in a tandem MS experiment. The plot on the right sketches the internal energy distribution after ionization. In EI, the distribution is broad and centered at high energy, extensive fragmentation. In ESI, the distribution is sharp, and at low energy, the molecular ion survives. Soft ionization was the great breakthrough that enabled biomolecular mass spec. Before ESI and MALDI, you could not ionize a protein without destroying it. Since ESI and MALDI, we can routinely measure intact mega-Dalton complexes. Entire fields, proteomics, metabolomics, depend on it. We'll do the details in the next lecture. For today, just hold the hard versus soft distinction in your head. Brief note and preview of Module 3. The mass analyzer. The job of a mass analyzer is separation. Take a beam or a population of ions with different mass-to-charge ratios and separate them in space or in time or in frequency so that the detector can count them separately. There are 6 commercial analyzer types, each with its own physics. Magnetic sectors deflect ions on circular arcs with a radius that depends on the mass-to-charge ratio. Quadrupoles act as RFDC mass filters, letting only one mass-to-charge ratio through at a time. Ion traps do what they sound like. They trap ions in a small volume then eject them selectively. Time of flight gives ions equal kinetic energy and times their flight. Light ions go fast, heavy ones go slow. The orbit trap is an elegant recent invention where ions orbit a central electrode at a frequency that depends on the mass-to-charge ratio. An FTICR uses ion cyclotron motion in a strong magnetic field. The frequency again depending on the mass-to-charge ratio. Each of these has a different sweet spot in the trade-off space. A quadrupole is cheap, fast, durable, but only reaches unit resolution, meaning it can separate the mass-to-charge ratio 200 for mass-to-charge ratio 201, but not mass-to-charge ratio 200.00 from 200.05. An orbit trap delivers 100,000 resolving power at routine speed, costs $500,000. An FTICR reaches 1 million resolving power, but is expensive and relatively slow. The table gives you the order of magnitude for each choice of analyzer. Is a matter of matching these specs to your problem plus your budget. Finishing the architecture tour with modules 4 and 5. The detector's job is deceptively simple. When an ion arrives, register its arrival as an electrical current pulse. In practice, we're counting single ions much of the time, so detectors need tremendous amplification. The most common detector is the electron multiplier. When an ion hits the first surface, it kicks out several electrons. Those electrons are accelerated and hit a second surface, kicking out more, and so on through a cascade of diodes. By the end of the cascade, a single ion has become a pulse of about 1 million electrons, easily measurable. Microchannel plates are the high-speed version used in time-of-flight instruments where you need nanosecond scale timing. Faraday cups are used when you have a very intense ion beam and you want stability rather than sensitivity. They're slow, but don't drift. The orbit trap and FTICR use a completely different detection scheme called image current detection. The ions themselves aren't consumed. Instead, you detect the tiny electrical currents they induce in nearby electrodes as they oscillate. You then Fourier transform the signal to get the frequencies and thus the mass charge values. This is non-destructive and gives very high resolution. The data system. Module 5 is essentially a computer, but it's worth appreciating that a modern mass spectrometer is as much software as hardware. The data system controls every single parameter of the instrument, digitizes the detector signal at up to 1 gigahertz, builds the mass spectrum, builds the chromatogram, runs library searches against databases of tens of thousands of reference spectra, and deconvolutes multiply charged envelopes to give protein masses. In practice, a modern LC-MS run generates anywhere from 100 megabytes to several gigabytes of data. Learning to work with this data is a significant part of the skill set for an MS-based analytical chemist. Now we come to the one piece of physics that's truly essential for the rest of the module: why mass spectrometers need vacuum. The issue is straightforward. Inside the instrument, we want ions to travel from the source to the detector, typically a distance on the order of 1 meter, on a well-defined trajectory. That trajectory is set by our electric and magnetic fields. If an ion collides with the neutral gas molecule along the way, several bad things can happen. The issue is straightforward. Inside the instrument, we want ions to travel from the source to the detector, typically a distance on the scale of 1 meter, on a well-defined trajectory. That trajectory is set by our electric and magnetic fields. If an ion collides with the neutral gas molecule along the way, several bad things can happen. First, the collision changes the ion's momentum. Its trajectory is now off. The mass analyzer doesn't work. Second, the collision might transfer the ion's charge to the neutron. Now, our ion is neutral and we can't detect it. Third, the collision might involve chemistry. Ion-molecule reactions that produce new species at new mass-charge ratio values. We get artifacts in the spectrum. Fourth, even glancing collisions scatter ions off axis. We lose signal. At atmospheric pressure, these collisions happen about 10 billion times per second per molecule. No ion survives even a nanosecond scale journey. So we need a vacuum. How low? The relevant physical quantity is the mean free path, the average distance a molecule or ion travels between collisions. The kinetic theory expression is straightforward. lambda equals kb times T over square root of 2 times pi d squared times P. kBT is the thermal energy, D is the kinetic diameter of a gas molecule, P is the pressure. The relationship is simple. The lower the pressure means the longer the mean free path. For a mass spectrometer with an analyzer a meter long, we want the mean free path to be comfortably longer than the analyzer, say 10 meters, so that the vast majority of ions make it through without collision. That requires pressures below 10 to the minus 5 millibar in the source and below 10 to the minus 7 millibar in the analyzer. We'll continue this explicitly on the next slide. Let's work through the mean free path calculation so you can see the numbers. We want the mean free path of nitrogen gas at room temperature. Nitrogen, because air is mostly nitrogen and it's the dominant residual gas. The collision diameter of nitrogen is about 0.37 nanometers. 298 Kelvin is the room's temperature, and we'll compute lambda at 4 different pressures spanning the range of interest. The setup is straightforward. Kb times T at 298 Kelvin is 4.1 times 10 to the minus 21 joules. Pi d squared is 4.3 times 10 to the minus 19 meters squared. The square root of 2 pi d squared factor is 6.1 times 10 to the minus 19. And remember to convert millibars to pascals. 1 millibar is 100 pascals. I plug in the pressures. At 10 to the minus 3 millibar, which is what a simple pump, rough pump gives you, the mean free path is 68 millimeters. That's far too short for an MS analyzer. An ion would collide within the first few centimeters. At 10 to the minus 5 millibar, which is what a turbomolecular pump routinely delivers in the source region of the instrument, the mean free path is about 7 meters. That's perfectly adequate for the source. At 10 to the minus 7 millibar, the typical analyzer pressure, the mean free path is 680 meters. That's comfortably longer than any analyzer could possibly be. Excellent vacuum, excellent performance. At 10 to the minus 9 millibar, sometimes called ultra-high vacuum, the mean free path is 68 kilometers. This is overkill for most purposes, but is required in ion storage experiments where you want to trap ions for seconds or even minutes before measuring them. The practical takeaway: a modern mass spectrometer has at minimum 2 pump stages. A rough pump to get you from atmospheric pressure down to about 1 millibar, and then a turbomolecular pump to get you the rest of the way down. Most complex instruments use differential pumping with 4 or even 5 stages, so you can have an open electrospray source at atmospheric pressure on one end and an analyzer at 10 to the minus 7 millibar just downstream. This slide shows the pressure gradient in a modern LCMS instrument, which is the extreme case because the ion source operates at atmospheric pressure. Look at the scale. We start at 1000 millibar in the atmospheric pressure ion zone. We end at 10 to the minus 7 millibar in the analyzer and 10 to the minus 8 in the detector. That's a pressure reduction of 12 orders of magnitude over a distance of maybe half a meter. How is this possible? Differential pumping. The instrument is divided into chambers separated by small apertures called skimmers. Each aperture is typically a hole 100 micrometers in diameter. Ions travel through the hole. Gas, being omnidirectional, mostly does not. Each chamber has its own vacuum pump. Reading left to right, the first stage, called the interface, drops from atmospheric pressure to about 1 millibar. That's a rough pump at the outlet of a heated capillary. Next stage drops to 10 to the minus 3 millibar. A small turbo pump handles this. The ion optics region is at 10 to the minus 5. By the time we reach the analyzer, we're at 10 to the minus 7. The detector is 10 to the minus 8. In a lab setup where you can hear the pumps running, this is why a mass spectrometer sounds like a small airplane when it's on. Several pumps, each with several kilowatts of power, keeping these pressure differentials intact. The engineering is impressive and understanding it matters because vacuum leaks are the single most common cause of MS instrument downtime in the real world. A tiny leak anywhere in the chain ruins performance everywhere downstream. Now let's define our key performance metrics carefully, starting with the most fundamental, mass to charge ratio. The definition is simply the mass of an ion divided by the number of elementary charges it carries. So an ion of mass 100 Daltons with a single charge appears at mass to charge ratio 100. The same mass with 2 charges appears at mass to charge ratio 50. A point of terminology: the mass unit we use is the Dalton, symbol DO. It's defined so that a carbon-12 atom has a mass of exactly 12 Daltons. 1 Dalton is about 1.66 times 10 to the minus 27 kilograms. You'll sometimes see the atomic mass unit U used interchangeably. They are identical. Chemists tend to use Dalton, physicists sometimes use U. Don't let the switch confuse you. Look at the examples. The water radical cation and the ammonium cation both appear at mass to charge ratio 18. They happen to share a nominal mass, but they're different species. The calcium diction has mass 40, but charge 2, so it appears at a dication at a mass charge ratio 20, mimicking a mass 20 species. Glucose with a protein attached gives a mass charge ratio 181. Insulin with 5 protons attached to common ESI charge state gives mass charge 1163. An antibody with 50 protons attached, which is typical for ESI or of IgG, appears at mass to charge ratio 3000. Here's the big idea. The same molecule can appear at many different mass to charge values depending on charge state. For small molecules, this rarely matters because they ionize singly. For proteins and large polymers, you can get a whole envelope of peaks at different charge states, and interpreting that spectrum means deconvoluting the envelope to get the underlying mass. We'll work through a deconvolution example in the next lecture. Resolving power, usually called R, is the single most important specification of a mass analyzer. It tells you how well the instrument can separate two peaks that are close in mass to charge ratio. The definition is very simple. R equals m divided by delta m. Here m is the mass at which you're measuring, and delta m is the width of a peak at that mass. The width is usually the full width at the half the maximum height, abbreviated FWHM. A caveat on conventions. The older literature, especially from the sector instrument era, used what's called the 10% variance definition. That's the mass to charge separation at which two equal height peaks just touch 10% of their maximum, meaning there's a small dip between them. The full width to half maximum R is roughly twice the 10% value R for a typical peak sheet. Then you read specification sheets. Always check which convention is being quoted, especially for older instruments or technical literature from the 20th century. Modern vendors almost always use FWHM. The graph on the right shows two Gaussian peaks at mass to charge ratio 100 and 100.1. Their full width half maximum is about 0.047, so their R is about 100 over 0.047, which is around 2000. That's good enough to separate the two peaks with clear baseline between them. In practice, rough resolving power values by instrument type. Quadrupole around 2000, ion trap up to about 10,000, time of flight up to 50,000, Orbitrap up to 500,000, FTICR over 1 million. Each factor of 10 in resolving power typically costs you roughly a factor of 10 in instrument price. The key practical question is always is my R high enough for this problem? If I have two candidate compounds with theoretical masses 500.20 and 500.22, I need an R of 25,000 or better to separate them. Remember that number when we get to the worked examples. Mass accuracy is how close the measured mass to charge ratio is to the true value. We always express it in parts per million because the fixed Dalton error matters more at low mass than at high mass. 2 millidaltons off at mass to charge ratio 100 is 20 ppm. 2 millidaltons off at mass to charge 10,000 is only 0.2 ppm, much tighter. The formula is simply observed minus theoretical divided by theoretical times 10 to the 6th. Practical benchmarks. A quadrupole is essentially nominal. It measures to the nearest Dalton, which at mass to charge ratio of 500 is about 2000 ppm error. That's why we call quadrupoles unit resolution instruments. Time of flight and orbit trap are what we call high resolution accurate mass, or HRAM. A modern QTOF delivers 2 to 5 ppm accuracy routinely. An orbit trap routinely hits below 1 ppm. An ICR with a well-calibrated instrument can achieve 0.1 ppm. The 5 ppm rule is worth memorizing. This is the accepted regulatory criterion in ICH guidelines and an EU Commission decision 2002-657-EC for confirming the identity of a compound from its mass alone. If your measured mass is within 5 ppm of the theoretical monoisotopic mass of the candidate formula, that's considered a confirmatory match. Tighter than 5 ppm is, of course, better. The example is a pentamer peptide. We measured mass to charge ratio 418.2235. The theoretical mass of the proposed M plus H is 418.2235. 0.2240. The difference is 0.0005 Daltons. That's 1.2 ppm, which passes. How does all this matter? Because at low mass accuracy, dozens of or hundreds of molecular formulas can match a given nominal mass, 2 ppm accuracy. Typically, only 2 or 3 formulas match for molecules below about 500 Daltons. Three more metrics complete the essential spec sheet for any mass spectrometer. Sensitivity, dynamic range, and speed. Sensitivity is signal per unit analyte. The best way to think about this is the amount of analyte on column in a chromatographic run that gives a signal-to-noise ratio of 3, the classic detection limit. For a simple quadrupole in full scan mode, that's about 1 picogram on column. For a triple quad in MRM mode, it's about 1 femtogram. So a factor above 1,000 better. For a modern Orbitrap in targeted mode, you can get down to around 100 attomoles, and advanced techniques like nanoelectrospray into a Q extracted HF can reach septomole. That's 10 to the minus 21 moles, individual molecules essentially. Dynamic range is the ratio between the largest single signal you can measure and the smallest A. A typical MS run gives 3 to 5 orders of magnitude of linear range. That matters for problems where you have a major component and trace components to quantify in the same sample. Say a pharmaceutical impurity profile where the active ingredient is 99%, but the impurities are at 0.1%. Speed is how many mass spectra the instrument can acquire per second. A quadrupole in MRM can do 10 to 20 transitions per second, multiplexed. A time-of-flight instrument pulses at kilohertz rates. An Orbitrap does roughly 1 to 10 spectra per second at high resolution and faster at low resolution. And here's the trade-off triangle, which you should internalize. You can optimize any two out of resolving power, sensitivity, and speed. Getting all three simultaneously requires the most expensive instrument on the market. Higher resolution generally costs acquisition time. Higher sensitivity generally means you've optimized for a single mass-to-charge ratio rather than a full scan. Be skeptical of any vendor that claims all three at once. Something is always given. The practical reality in the bottom is that a chromatographic peak in modern LC is about 6 seconds wide. For reliable integration, we need at least 12 data points across the peak, meaning the MS cycle time can exceed half a second. That half a second has to cover every acquisition, every transition, every switching overhead. Method development in mass spec is largely the art of squeezing everything you need into that budget. Mass concepts. We have to be careful when we say mass because there are actually 3 different masses for any molecule, and you need to know which one applies in a given context. The nominal mass uses integer atomic masses. Carbon 12 is 12, hydrogen 1 is 1, and so on. The monoisotopic mass uses the exact mass of the most abundant isotope with that element. For organic compounds, that means all carbons are carbon 12, all hydrogens are protium, all nitrogens are nitrogen 14, so on. This is the sum you compute when you're interpreting a high-resolution mass spectrum, and it's what the dominant peak corresponds to for small and medium molecules. Is almost always what you want. The average mass is the number in the periodic table it gives you. It's weighted by the natural isotope abundance, which means the carbon's average mass is 12.0107. The example works out nicely for caffeine. The nominal mass is 94, monoisotopic is 94.08, and so on. But now scale up. For a 2 kilodalton peptide, the gap is about a full Dalton. For more, it becomes 80 Daltons, which is enormous when you're reporting the mass of a protein and you confuse monoisotopic and average. You can be 80 Daltons wrong on a molecule where the relevant biological modifications are 16 or 80 Daltons. It matters. The rule of thumb, for small molecule high-res work, use monoisotopic. For large proteins with unresolved isotope envelopes, use average. For mental arithmetic on a napkin, use nominal. Isotope patterns. So a brief introduction to isotope patterns, which we'll develop much more in lecture 4 when we do spectrum interpretation. But it's useful to have the concept now. Every element that appears in a mass spectrum brings its natural isotope distribution with it. Carbon is 98.9% carbon 12 and 1.1% carbon 13. In a spectrum, for every main peak from a pure carbon 12 ion, you see a smaller peak, 1 Dalton higher than the carbon 13 isotope alone. Same molecule with 1 carbon 12 replaced by a carbon 13. The height of that M+1 peak gives you information about how many carbons are in the molecule. Hydrogen and nitrogen or oxygen are mostly one isotope. Sulfur is a substantial sulfur 34 peak, 2 Daltons above the main at about 4%. That's useful. But chlorine and bromine are the stars. Chlorine is 3 to 1 chlorine 35 and chlorine 37. So for every chlorine-containing ion, you see a peak 2 Daltons higher at 33% of the main. If you see 2 chlorine atoms you get a 3-peak pattern in ratio 9:6:1. That's just binomial expansion of the 3:1 ratio. Bromine is almost 1:1. So bromine containing ions give 2 peaks of nearly equal height separated by 2 daltons, which is very characteristic. The isotope pattern is often the single most diagnostic feature of an EI or ESI spectrum, and you can look at the spectrum and immediately recognize, oh, that's a chlorine-containing compound, or that molecule has 2 bromines, just from the shape of the main peak info. We'll come back to this in full detail with worked examples in lecture 4. On to our worked example. So here we'll work together with this. The scenario comes up in a real analytical. Monitoring carbon monoxide at low levels in air is a legal requirement in many industrial settings. The problem, carbon monoxide. CO has a nominal mass 28, but so does molecular nitrogen, N2. If we put a gas sample into a mass spectrometer, will this instrument see 1 peak at mass to charge ratio of 28, 2 peaks? Step 1, compute the exact masses. Carbon 12 is exactly 12. Oxygen 16 is 15.99491. Their sum is 27.99491. Nitrogen 14 is 14.00307. 2 nitrogens give 28.0060614. So the difference here is seen, and this means that we have the same nominal mass but different exact masses. So we ask the question, how much resolving power do we need? The formula R equals M over delta M is about 28. Delta M is 0.01123, so R required is about 2,500. Then let's match this to the instruments. A quadruple maxes out at around 2,000 R. That's not enough. A quadruple sees the two species as a single peak at a nominal mass to charge ratio of 28 and cannot tell them apart. An ion trap might do it in a good day with careful optimization, but a TOF, Orbitrap, or FTICR easily resolves it. The practical consequence is that if you need to measure CO in air at trace levels, you cannot use a cheap quadruple GCMS. You need a high-resolution analyzer. This is one of the reasons the continuous emissions monitoring in the power industry uses high-resolution instruments. The broader lesson, and this is the point I want to internalize, the nominal mass is not the whole story. Two molecules with the same nominal mass can be separated at high enough resolution. As resolving power rises, mass to charge ratio becomes a near unique identifier for molecular formula. That's why HRMS has transformed the field. The information content of an exact mass measurement goes up exponentially with resolving power. Here are the practice problems. I encourage you to do them yourself, and the solutions will be posted. And here's the summary of the next lecture, where we will look at ionization sources. And thank you for listening.